Yeah, that's excellent.
All right, we're done.
Good to go. Well, we'll see.
Usually give 5 minutes. People come with coffee here.
What was absolutely essential.
Oh, the coffee is the snacks. All right, let's begin. Thank you very much, everybody, for coming. Today, we welcome Sergei Kalinin, who is Weston Fulton Chair Professor at the University of Tennessee. But before that, he spent 20 years in Oak Ridge National Lab and was on a sabbatical at Amazon. So Sergei has a lot of interesting awards. So for example, he had Feynman Prize in 2022. He also had Blatnick Award for Physical Scientists in 2018, Hermes Medal for Scanning Probe Microscopy in 2015, and many, many more. Right? So Sergei has an amazing record in publication. Has more than 600 publications and like more than 100 H-index, something like this, right? Unreachable. He also is a fellow of MRS, APS, American Institute of Physics, IEEE, ABS, and Forsyth Institute. His degrees came from Moscow State University and then PhD from University of Pennsylvania before he joined Oak Ridge.
Mm-hmm.
Okay.
Yep.
So at this point, let's welcome Sergei.
Thank you very much for the introduction and invitation. So it's a great pleasure to be here. So as you can imagine, a large number of publications was important kind of year ago. In the coming years with the things like ChatGPT, that's going to be probably different metrics because that stops being quite as big as an accomplishment. But at least it illustrates that I have been doing science long enough. And today I would like to talk about the automated experiment and scanning probe and electron microscopy, focusing more on the opportunities that emerge in the interface between the physical sciences and the machine learning. So as Jarek have illustrated, I got my degree at UPenn, then I moved to Oak Ridge, where I worked for almost 20 years, starting as a Wigner Fellow and leaving as the corporate fellow. Then, as many people before me, I decided to move full-time to academia. But the slightly unusual thing was that I've been working in machine learning physics for 15 years. And I decided to spend some time and see how the basic science becomes technology. So I spent a year in Amazon in the special project divisions. Now, what I would like to talk about today is the autonomous microscopy. And one very important thing is that when someone tells you, hey, let's do machine learning, or let's do something automated, the first question to ask is, what is that you want to accomplish? Like, why would you want to do that? So in microscopy, this is fairly straightforward. So microscopy is basically mainstay in areas such as material science, condensed matter physics, biology. There are probably something like hundreds of high-end electron microscopes and tens of thousands in the world. There are thousands of high-end SPMs. There are over 50,000 ambient SPMs. So the market size for electron microscopy is about 3 billion, and due to the whole thing prior, it actually goes up. Market size for the scanning probe microscopy is about 700 million. But the interesting thing is that most of the time, what microscopists do is they sit alone or almost alone in the dark room, and they turn knobs, right? That's kind of what you do. Admittedly, the technology develops, so the room doesn't have to be dark anymore, but the principle of the matter stays. And at the same time, for the last maybe 10 years, there was a lot of enthusiasm about automated cars, automated image analysis, and therefore quite a lot of people have come up with the ideas, let's make an automated microscope, sort of analogously with the autonomous cars. And this becomes the first, maybe not a red flag, but a yellow flag. So when do you think Elon Musk promised to have the fully autonomous cars on the road? Does any of you remember? So the first time it was like, okay, it will be done by 2017. That obviously did not happen. In fact, the latest news that Tesla is further away from autonomous cars than they think they are even now. So around 2014, at the time when the deep learning was becoming big, the really visionary figures like Hinton were saying by 2020 there would be no job for the radiologists in medicine. All the image analysis would be done by the deep learning. So what is common about these two predictions? So none of this materialized, right? So which means that using machine learning for something in the real world may be a little bit different, a bit more difficult than people believe in it. So going back to microscopy, we want to understand why automated microscopy and why automated microscopy is useful. The first and fairly superficial step of analysis is that we need to look what does microscopy do. And given the excellent AI facilities here run by very esteemed Professor Dr. Falke, whom I have the pleasure of knowing for 15 years by now, all of you have experience working there. So you go to the room, you feel the instrument, then you find some place that you think is interesting, right? Then you do the overall imaging, you zoom in, you zoom out, you find another region, you zoom in, you zoom out, then you zoom in further, and then you start to take some spectroscopy. So it can be of sim spectra, it can be some form of field response spectroscopy, it can be IV measurements, whatever. And after you get a lot of data, you come back home, you take the data, then you analyze the data after it has been acquired. Obviously, we'll go through it a few more times, but obviously this approach has a very significant limitation. And the limitation is that you constantly use your judgment as a scientist to make the decisions to run the microscope. And while doing it, you convey some set of instructions to the microscope. So the question that I asked myself about 5 years ago is, can I do this type of analyze and implement this workflow using the machine learning as a part of the navigation tool? So that's kind of automated microscope. And here comes a very interesting point. So you always have to ask a question, why are we even doing that, right? Microscopy is not done for the sake of microscopy. You do microscopy to learn something about material and gain some insight about what happens inside this material, why the properties are what they are, and ultimately get the feedback to material synthesis and utilization. So microscopy is not a goal in itself, it's a means to larger goal in science. However, it is very useful to analyze the decision-making process of the person running the instrument. So imagine that I'm sitting in front of the microscope and I'm taking this image. And I want to study the piezo. Wonderful. Actually, it's not here. It's actually on this instrument, on this. And you want to learn something about the material. So where do you start? So first of all, if I image this ferroelectric domain pattern and I want to measure the history of the switching, I would interestingly start with the dark regions. I know that these regions are not interesting. However, kind of hopefully being a good experimentalist, I want to make a baseline for my instrument operation. After that, I look at this image and I say that these striped domains occupy most of the image part. Therefore, it is natural for me to choose these regions to explore in some detail, but if the spectra in these images are all in these regions are all the same, I will say that now I have representative information about structure property relationship in the system. After that, I can say, hey, these domain patterns look interesting. These are clearly an outlier. So maybe I want to take my measurements here. But some of my colleagues will say, you know what, this is very superficial logic. Like you shouldn't be like a 10-year-old or 5-year-old going for something that looks fancy. You should have some theory about why you're doing research. And in this particular case, I know that there is a crystallographically incompartible region, so there can be some interesting physics out there. Some of my other colleagues can say that, look, there is a ferroelectric domain wall. This is the region where the domain wall is bent, and therefore there may be some infestation of flex electricity. So now, why do I tell you that? 2 reasons. First of all, you can apply this logic for any other imaging tool that you run. You use the same logic when you do yields and you look at the electron microscopy. Use the same logic when you use an optical microscopy and choose what region to study by top series. Use the same logic if you look at the sample and you want to pick up what the areas are from atom from. This logic is common across all physical characterization. There is another reason why I'm telling you that. Imagine that I said that when we run an automated experiment, we need to have what machine learning people call the reward function. What is that we want to learn? So autonomous car, relatively speaking, has only one reward function. It's supposed to take you from point A to point B without crash and in the smallest amount of time. It's a very simple reward. Implementation is a different story. Let's not go there. But the purpose of the experiment is straightforward. Science is not like that. So even in a very simple experiment where I effectively run my microscope by point and click, my reward function changes throughout the experiment. So now imagine that you want to collaborate with somebody who does machine learning, and you need to somehow convey this knowledge of your decision making to the machine learning algorithm. It's not going to be easy because in the beginning, my actions are informed by the knowledge of how the microscope works. In the middle, they are driven by statistics. Machine learning can do that, or finding the outliers. And then they start to be driven by pretty significant physical theory. So that's actually difficult. Machine learning cannot do that very well. More importantly, I can easily come up with experiments that human cannot do. So imagine that I ask myself a question that, look, I see this ferroelectric domain pattern. I want to understand what type of ferroelectric domains manifest here, here, or here. That's relatively easy. I just need to find the simulation. But imagine that I ask this first question. So what type of microstructure do I need to find so that the hysteresis loop closes to this one? So this is the inverse problem. It is not easy problem. So currently we solve it by taking the measurements everywhere using the shotgun approach and then sorting out the results. But there are a lot of measurements where shotgun approach is not applicable, either because measurements are expensive or because the measurements are destructive. So TFM is okay, but if I wanted to explore the composite using the non-indentation to find the region with a specific indentation curve, I cannot do it on the grid. So if I do non-indentation, then everything around is destroyed. So that makes scanning probe microscopy kind of complicated. The application of machine learning in automated SPM is complicated. However, if you learn to solve this type of problems, you start to instantly get a lot of low-hanging fruit. For example, if I run scanning probe microscope or electron microscope, I want to explore the image plane of the sample, the two-dimensional parameter space. Guess what? If my colleagues run the automated synthesis lab when they use the robot to synthesize the hybrid perovskite, they effectively explore the binary, tertiary, or quaternary phase diagram. That's also an exploration of the low-dimensional parameter space. The machine learning solutions that work for one, with some degree of approximation and adaptation, will work for another. If you collaborate with the theorists who, for example, explore the quantum computing and study the parameter spaces of some Hamiltonian, that's also an exploration of fairly low-dimensional parameter space, even though it can take forever. And the area which I find most interesting from scientific point of view now is the place where scanning probe microscopy and material science come together. The example of this area is the combinatorial libraries. So if you think about it, it's a magic, right? So you can create a sample which have a gradation, which has a concentration gradient. It basically means that you are crossing the line across some interesting regions of the phase diagram, which means that all the interesting physics of these materials, like formation of the Mercatropic phase boundary, is encoded somewhere on this sample. So in some sense, the sample contains pretty signatures of pretty fundamental physics. You can study this physics if you take this sample, make an electron microscopy sample and image the ferroelectric domains, or map it using TFM or using any other method. But there is a catch, right? If it were possible to take the electron microscopy measurements every 5 microns, I would have a beautiful idea about how the physics of morphotropic systems work. The catch is that electron microscopy is a very expensive method, which means that this is not going to be viable. I cannot do that. Which means that I need to be a little bit smarter about my experiment, meaning that I need to do measurements here and here, and then I need to have some strategy to find the next point for the measurement. And based on that, refine the location for the next point. So I need to learn the physics that contained in the imaging data, and I need to feed it into the understanding of how the material system works. So can machine learning help us here, right? Excellent question. Machine learning is everywhere. So there are several interesting things about machine learning. So first of all, of course, machine learning existed for quite a while. So I started to work on it more or less seriously in 2005. But machine learning has come up to the forefront of attention almost exactly 10 years ago. So that was the time when the deep learning was demonstrated on the ImageNet, and this field usually exploded. And the last 10 years was almost incessant increase, emergence of the new architectures and new capabilities from generative adversarial networks and out encoders to AlphaGo to transformers. So for the year 2023, it's obviously ChatGPT and the large language models. So there's always something new. The interesting part, however, is that the progress and the impact of the machine learning for experimental physics or material science has been very minimal for the time being. It's a great thing, but for many of us, they exist in some different universe. So they're not with us in the lab, they're somewhere out there. Even though ChatGPT is, of course, a different story. So the question is, why is machine learning in physics different? But the answer is that, first and foremost, it requires domain expertise and domain-specific goal, right? I gave you an example of autonomous car. So people who do machine learning know what the autonomous car should do. People who do machine learning don't know what the microscope should do. It's not a defined goal for them. Secondly, machine learning, by far and large, is based on what is called the big data. So big data has nothing to do with the volume of the data. It has to do with how well the data supports the generative parameter space. But generally, it is big one way or another. In physics or material science, we almost never have big data, right? So you cannot go to the lab and prepare 10,000 samples. That's the point where you kind of prepare or think about getting a different PhD advisor. So we deal with very small experimental budgets. And another, in exchange, physics is based on the physical laws, on the kind of basic or phenomenological relationships. And physics is heavily hypothesis driven. All of these elements are not a part of the classical big data culture. There are other things. So big data or machine learning, it's a culture, it's not a method, it's a culture based on infrastructure, open code, and open data. This is not common in many scientific areas. If you approach electron microscopists 5 years ago and say that the data should be open, you are not going to get understanding as the feedback. And most importantly, science is not a process of exploring the static data. So science is a dynamic process. We ask questions to the universe, we apply experimentation, we get some answers, we try to understand these answers as much as we can, and based on this understanding, we build the models of the universe. And build on these models, we formulate the hypothesis of what is out there, and we ask two set of questions. So this is a dynamic process, and this is not what machine learning does. So interestingly enough, big companies such as Microsoft, Meta, Google, NVIDIA, all of them started to go into what they call ML for science. But if you look carefully at their effort, you will see that all of them try to combine machine learning and theory, which is a kind of only the half of this great cycle between theory and experiment. Which interestingly means that that's a time of opportunity for all of us, because now ML is kind of almost there to apply for experiment. Now, going back to the automated microscopy. Another question that you should always ask if somebody tells you, let's use machine learning for something, the first question should be, can we do it without machine learning? Is it even necessary? And that was a very humbling experience for me, because once we start to think about automated experiment in SPM, the first prototype that we built, what we call Therabot, is a type of technique that could have been realized 25 years ago. So the idea was very simple. If we switch ferroelectric material, we have to process it. One is nucleation of the domains. Another is the domain move motion. When we run the normal experiment, these processes happen at the same time. Can we separate them? Turns out that it's very easy to do so. All we have to do is to take our AFM, scan the line on the surface, and when we detect the presence of the ferroelectric domain ball, we apply a voltage pulse. Very simple experiment. It actually does remarkably good job in separating domain wall motion and the domain nucleation. So these are kind of movies when we only move the walls but don't nucleate the domains. And technically, it could have been done 25 years ago. Now, why is it humbling? It's humbling because I worked on PFM for 25 years. And I knew that this is an important problem since basically the first year I was doing it as a graduate student. And I never thought about it for 20 years after doing PFM, even though it does not require anything rather than really to realize it. So the first thing is that you really need to think kind of out of the box in the problem-oriented way, rather than say, hey, I need to learn machine learning. Machine learning is useful, but it's a technique, not an approach. Of course, you can do more complex things. So if you have the engineering control, again, without machine learning, you can run the experiments where you take an image, find on the domain walls, identify the regions with the high domain wall curvature, and then you tell your microscope to go and take the measurements only at these regions one by one. Again, there is no machine learning here, it is just the engineering of the instrument. And it already gives you a very useful information. Admittedly, you can get much further if you actually add machine learning. And this is the example done about 2 years later, when we have a commercial microscope that streams the data. This data is analyzed using the ensemble deep convolutional network to produce the pattern of the ferroelectric domains. So you can say, hey, that's a simple problem, right? These are just dark lines. So all you have an edge filter here, I can do it with a tiny filter in the circuit image. It's almost true, but if you look at this image carefully, you see that there are two types of dark lines, right? These ones, somewhat diffuse, and these ones, which are much more sharper. Notice that our neural network recognizes these lines, but it basically totally ignores these lines. So this is actually much more complicated than it seems to be. And this is exactly the type of development of this type of networks is complicated. So the reason why there are no autonomous cars is because the computer vision algorithms don't adjust very well for the change in the lighting condition and the kind of unusual events. So the same problem exists in the microscopy. So building a network that is capable of analyzing the streaming data is actually fairly complicated. But once we have it, we can start to run very cool experiments. So we can take an image, we can identify the domain walls, we can define our measurement grid, we can take a measurements like this only at these domain walls, and then we can map, for example, the height of the hysteresis. And you can see that we see some variation across our measurement points. For example, here they're brighter, here they're darker. We understand this because this domain wall is tilted. But we also see things that we don't understand. For example, it changes from bright to dark along this domain wall. We can speculate that it has to deal something with the peak domains, but we don't know for sure. So can we run these measurements in the grid? Theoretically, yes, but not really, because if we try to run the measurements on the grid, most of our points would be useless. They would be either inside the domains or not. And secondly, our measurement points will not have a perfect alignment with the ferroelectric domain boundaries. Can it work for other techniques? Of course. So we can run the same type of approaches for electron microscopy. In fact, in some sense, it is much easier to apply machine learning for electron microscopy than for SPM. Because when you apply machine learning to physical systems, there is a thing called inferential physical biases, meaning how well do you know what the answer should be. So if I work with electron microscopy data, I ultimately expect to find atoms. So this is as fundamental as it can be. And I know that atom is essentially just a function. It's not a sausage or torus or whatever. When I look at the sample image in the scanning probe microscope, I mean, I have my expectations, but life can be more surprising on the mesoscopic scale. But this is the example where it works. So this is a hole, this is a graphene, this is a silicon atom that are dancing on this hole. This is what the deep convolutional network can do with that. So it takes this data and produces this one. Notice that this was done in the 2017, so very early on in the machine learning era on the data acquired after the experiment. And it took us 4 years to learn how to do this type of things in the real time. So this is the plugin for the Neo plugin. So here you have the data stream, and here this is the network that converts this video stream and the atomically segmented image. So a very interesting thing that happened in the last 5 years is that the activation barrier for running this type of experiments dropped pretty. Sorry, yes, not enough coffee in the morning. So 5 or 10 years ago, you really need to have a team that has access to the instrument internal operation. You need to be able to somehow get around the service contract. So the first time we deployed ML on the electron microscope with the 200K service contract, there was a little bit of trepidation in the process. But now it's very different. Now many instruments are coming with the Python plugin. So it's not a matter of having a large team to enable this instrumentation. It's a matter of finding the right tool and work with the manufacturer to ensure that you have access. So in other words, something you can do. And once we can do that, we can do a very cool experiments. For example, for the 2D materials, we can move the electron beam along a certain line, kick out the specific sulfur atom and kind of write letters. And about 5 years ago, my colleagues and I shown that we can actually use the electron microscope to manipulate atoms and move them around, build structure. So that was done about 5 years ago, and then this progress stopped. The progress stopped because humans are very slow compared to the electron microscope. The electron microscope operates on millisecond time scale. Humans operate on minutes and tens of minutes. So one of the collaborations that I have now is with the Google Brain team that works on the development of the reinforcement learning algorithms that get deployed on the microscope to actually run this type of experiment, and that actually works. So it's something that's operational. You can do other things. So you can take data from the microscope and stream it to the computer. The caveat here is that you can take data, convert it to atomic coordinates, and put it in the simulation. The problem is that the simulation takes a lot of time. So electron microscope is very fast. So we said, okay, now it works. Now it's time for theories to make theory better or faster at least. And we move to some other challenges. But let me talk a little bit about moving the next. So for the time being, I've shown you the examples of experiment. We know exactly what is that we want to explore. We use machine learning to help find it fast in real time. And then we want to explore it in detail. Notice that in this setup, machine learning is a pure engineering tool. It's essentially a version of the supervised ML. We gave the algorithm the examples of what we want to find, and then algorithm did it for us. So if you want to say that this is not science, it's engineering, then engineering is a great thing. I worked for a year in an engineering company. But you would be right, it's not a discovery, it's an engineer. Complicated, useful, that can increase your efficiency in the lab, but it's not scientific discovery. What if we want to do scientific discovery, right? That's why we're all here. So how that becomes a little bit more interesting. So let me show you an example of the concept. So if you are familiar with the Gaussian process, that's a great opportunity to evaluate my teaching skill. If you're not, and it feels totally weird and not understandable, that's actually normal. I worked with GP for about 3 years, and I started to understand and develop intuition for it only in the last 2 years. So for a year, I was doing it without understanding. But nonetheless, so kind of just bear with me for a second. So imagine that you want to learn something that you don't know, like some black box function. So the Gaussian process approach basically says the following. Let's assume that I do measurements in 2 locations. Very simple. You physically go to the lab and measure something. And then comes the part where you can become really suspicious. Based on those measurements, I'm going to reconstruct the surrogate function and its uncertainty. So if you feel deeply uncomfortable about it, you should. That's the right place to be uncomfortable. However, if you take it for granted that it is possible, then the next step becomes very easy. So if I know the interpolated function and its uncertainty, it becomes very easy for me to define my experimental strategy. For example, if I want to learn the function better, I should take the next measurement in the region where the uncertainty is maximum. So I just go to the place where my knowledge is least and I do the measurement there. And then based upon this measurement, I will reconstruct my function and uncertainty all over again. If I want to optimize the function, for example, I want to synthesize the hybrid perovskite with the best properties, In this case, I need to somehow balance uncertainty and prediction. So if I am greedy, I just want to do the greedy optimization, I will choose the place where the prediction is maximum. But if I want to balance exploration and exploitation, then I will somehow combine the prediction and uncertainty. So I go to the places where I expect better behavior, but I also explore the places where the better behavior can happen. So this is a very powerful technique. So we started to work on it before COVID, and we plan to use it for autonomous experimentation. Then COVID happened, so you're stuck at home for 6 months, nothing goes on, so there are no meetings because everybody is figuring out what to do, so you can focus on doing interesting science. So we applied it for theoretical models. So this is a phase diagram for Ising model with nearest neighbor, next nearest neighbor interaction. And here you see how the Gaussian process explores the phase diagram, trying to find the regions where the heat capacity is maximal. So this is the ground truth behavior. And here you see how the GP basically discovers it in real time. It's a very greedy algorithm, so it kind of locked on maximum and started to explore it. Then I said, great. So I told you that I spent a year doing Gaussian processing without understanding. So during this time, I did a lot of prototypes about how we can possibly use it for real microscopes. And it worked great on the pre-acquired data. So you kind of start to feel like it's going to work. Then it stopped being my work because my colleagues, Maxim and Rama, got access to the CNMS. So they put these three elements together. So Rama set up the DGX box connected to the instrument. He deployed the Maxim codes, and then they deployed the workflow that I developed. So we start to run it. And the first results start to come like this. So come on, here we go. So what you see here, this is the experiment. This is not the simulation. So you see how the scanning probe microscope measures the hysteresis slope. These are the measurement points. This is the Gaussian process prediction. And to be honest, this looks awful. This looks completely not like an image. In fact, after we compare the result of the Gaussian process working on the microscope to the ground truth, you can see that this is what Gaussian process does. This is what the ground truth image looks like. So if you come to the funding agency or even to the line management and say, look, we spent $500 million to set up the system, and now our instrument is fully automated, and this is what it measures, and this is how the world really looks like. That's maybe not a good message, right? Kind of looks awful. The question is why? The answer is that you have to go back to that part that was hopefully for your protest, that we reconstruct the function based on measurement, and you need to look at it as a little bit of detail. The problem with the Gaussian processes is they try to discover, to approximate the world through effectively a correlation function, which is learned during the experiment. That's what's called the kernel function. Unfortunately, it is exceptionally difficult to represent the data like this through the single correlation function. It has features on all length scales. So we realized that Gaussian processing is great, but it's absolutely not enough for what we are doing. It works only in low-dimensional spaces. The correlations are defined by kernel, which is very limiting. We don't use any knowledge about the physics of the system, and we also don't use any cheap information available during the experiment, so our proxy signals. Question becomes, can we do better? And then it turns out that it is the nature of the workflows in scanning probe microscopy to do better. Because when we run microscopy on some sample, it's never exploring a black box. We start from the image, and then we try to figure the location for spectroscopic measurements. It's not like pointing finger in the dark and trying to find out where the good regions are. Which basically means that if we want to come up with a machine learning workflow that is useful, it needs to utilize the same type of data as the human operator. That's exactly what we did with the thing called the deep kernel learning. So it's a kind of hybrid of the deep convolutional network that takes your image and image patches and compresses it down to the low dimensional embedding. And then you have a Gaussian process that runs on top of this embedding vector. So here the logic is the following. You start with a full image, you split it into the sub-images or image patches, and then for just one image patch, you do the measurement. And then you train your algorithm when you have all image patches and the measurements only at one patch. So see the point, it's we don't have all the data, we have data acquired sequentially. Then imagine that if you train it on one data set and then you run it on all the remaining patches. So what are you going to get? Of course, you're going to get the same prediction because you gave it only one example of how it's going to look like. So what's going to be different? The different thing is going to be uncertainty. Gaussian process gives you prediction and uncertainty interval. For the patches that look exactly like this one, uncertainty will be low, they're all the same. But the patches that are different, uncertainty will be high. Which basically means that we do the next measurement in the region that counts with a high uncertainty. And then we retrain our algorithm again. Now our certainty would be high for the domains that we already explored, and certainty would be low for the domains that we didn't explore. And then we can repeat this process over and over again. What's even more interesting is that we don't have to stay in the purely exploration regime. We can also find at that optimization target. I can run this algorithm when I not simply explore domains, but I also try to find the domain structures where the area under the loop is maximal. So again, I can do it for SPM, I can do it for electron microscope. So let's just look at the electron microscope example. So this is a flake of two-dimensional material. This is the yield spectrum. So this is the zero loss peak. This is the edge plasmon. This is the bulk plasmon. So let's assume that I tell my microscope to take the yield spectrum, cut off the zero loss peak, feed the remaining part by two Gaussian peaks, and use the ratio of the area on the first peak and second peak as our search criteria. So if we deploy this algorithm on the microscope, this is how the result will look like. So that's not a simulation, this is a deployment of the code of the active instrument. And all this work is effectively done by three people. One person who wrote the library, one person who defined the workflow, and one person who implemented it on the microscope and kind of make it roll. It doesn't require large teams anymore. So as you can see, the microscope have found the regions where the ratio of one peak to the second peak is maximized. And as you can see, these regions are on the edge, which can be predicted. So what if we run it on different places? So you can see that in all places we found the edge. For whatever reason, sometimes the microscope really likes the edge. So this one. Sometimes the microscope says, "Meh, I'm not sure, but maybe the answer is somewhere here. I'm just not sure about it." So there is clearly something in the data that we don't quite understand. But you know, we clearly discovered the new physics, but it's not an explainable physics yet. So can we control this operation? So kind of human in the loop type of approach. So let's say we can choose the different criteria. So rather than looking for the ratio of the first peak to the second peak, we just try to maximize the area under the bulk peak. So in this case, we explore the plane. So you can say, okay, maybe this is simple. It would work. Can it work for more complex systems? Yes, it can. We can run the same type of algorithm for the 4D stem, where we define our scalarizer and acquisition function from some characteristic of the tachogram. It works. So you can clearly see that the microscope finds something. So the points, acceleration points are not random. But in this case, we already don't understand what goes on, which kind of get to a fairly cynical joke after a few years, whether machine learning can discover new physics. And the answer is no, because if machine learning discovers something and we understand it, then it's not new. And if it discovers something and we don't understand it, then it's not physics. But in this case, it's very difficult to find something in between. But clearly, the method works. So if you want, we can look into more detail how it does it. So you see the exploration sequence, you see how the acquisition function evolves, how the prediction evolves, and how the uncertainty evolves. So we basically try to maximize prediction and take into account the uncertainty. So if the uncertainty becomes large, then this is the suspect region where we need to understand what goes on. So we can kind of at some point go through detail. Would it work for scanning probe microscopy? Why not? I mean, as I mentioned, the type of problems that I'm interested in are relatively insensitive to what type of imaging tool it is. So in this case, you have the algorithm running on the AFM. So this is the example of what it discovers. So if I tell my instrument to please find the regions where there is a largest on-field hysteresis loop area, it finds this fine. So this is our measurement steps from 0 to 200. You can see that algorithm explored the sample, and now it found that these regions are more open on this ferroelectric wall. If we do it in the off field, it says that all the interesting points are localized on this wall. And in this case, we can understand it because this is kind of close to what we expect for ferroelectric to behave. Of course, we can run it for different setup. For example, we can try to explore the non-linearity of the PFM response. And in this case, an algorithm clearly finds something. So this is the PZT, this is Hafnia, but in this case, we don't quite understand exactly what goes on. Now, I've shown you an example where we use the imaging data to guide the exploration of the physics, but the physics is encoded in some specific functional of the spectroscopic data. But there is no knowledge of the physical laws in the process. At the same time, imagine that you explore the phase diagram and you want to find out the dependence of the band gaps on the composition. So if you make the measurements on the end numbers, you typically will say, hey, there should be a linear relationship across the phase diagram. It's natural, yes. So physicists do this naturally. Data scientists generally don't do that. So that's kind of goes into the very interesting theory of the functional approximation, except that it's generally not rooted in physics. So can we incorporate the knowledge of the physics in our machine learning algorithm? This is where it becomes really interesting because there are excellent books about Bayesian optimization, for example, Roland Garnett, those that are really interesting, easy to read and understand. Most of these books introduce the concept of the Gaussian process as some combined multivariate normal. And then they say that, look, the Gaussian process has the mean function and the kernel function. So, and then it makes a very important statement. It says that we develop the general method. Mean function reflects the domain-specific physics, and therefore we will set it to 0. That's a statement which is done in pretty much all the books about Bayesian optimization that I read. And then the book will go in long detail about how you choose kernels, what type of spaces they operate on, and so on and so forth. But we are physicists, so we are not data scientists. So for us, mean function, the Gaussian process, is something that reflects our knowledge about the physics of the system. Which basically means that if I want to have a machine learning running on the microscope, I need to learn how to work with this mean function. So fortunately, when they started to work on it, my colleagues were able to implement the version of the Bayesian optimization with the non-zero mean function. So now you can do it with the PyTorch or X from Facebook, but at that time that was a new development. And this is how the difference look like. So if you do classical Gaussian processes, this is how your priors look like, this is how your posteriors look like after the measurement, and this is how the prediction with uncertainty look like. So this is the priors for zero mean GP, and this is how the priors look like for the GP with the probabilistic model. So you can say that my functions can be anything that has 2 peaks, and then you have a standard Bayesian priors of what the peak positions and distributions are. It's very, very powerful because this allows you to encode your prior knowledge of the physics of the system. And there's an example how it works. Okay. So this is an example of how simple versus structured GP will look like. So imagine that your ground truth is the black line. So it can be, say, band gap across the phase diagram. So you see that there is a rapid jump. Classical Gaussian processing is exceptionally bad in being able to follow this rapid jump because at the jump, your correlation length should become 0. So it basically can pinpoint the jump only at the cost of exploring the tails of the function at the same sample. This kind of becomes very inefficient. If you introduce the structured model that says that my function has 1 jump, I just don't know where it is, you see what's the difference. So you find the jump almost instantly, and then you spend the remainder of the time trying to explore the tails of the function. So knowing physics really makes the discovery much faster. And this advantage scales with the dimensionality of the problem. For example, if my ground truth behavior is this image, so this is a magnetization of Ising model, this is magnetic phase, these are non-magnetic phases. Classical GP will do measurements at these locations, kind of color-coded, and the reconstruction for classical GP will look like this. So not really good. But the structured GP will work like this. It will spend most of the time pinpointing the boundary between magnetic and non-magnetic states. So it's much, much, much more efficient. And our probabilistic model is basically that we have some magnetization, some regions where magnetization is 1, some regions where magnetization is 0, and there is a sharp boundary between them. So why is it useful? It's useful because in physics, we very often know the asymptotic behaviors for high temperatures, low temperatures, and so on. We just have an uncertainty where the phase transition is. So we actually have a partial knowledge. And structured GP allows us to actually implement this partial knowledge in our model. Then you can ask a question, look, when we do science, very often we have competing hypotheses, right? So we can have several possible models, usually more than one. What do we do in this case? So there is a long way, which is create a hierarchical model, which is computationally very intensive. There is another way, which is something that we call the hypothesis learning. And this concept basically evolved from combination of the philosophy of science and several summers reading and not understanding the books about the reinforcement learning. So the logic here is the following. Imagine that we have a system which is physical experiment. So it can be chemical synthesis, it can be film growth, it can be SPM measurement on the combinatorial library, it can be depositing context and doing measurement in the combinatorial library. It doesn't matter. It is a physical experiment. So let's assume that you do just one measurement and you send this measurement result to the Gaussian process model. At the same time, you inform this Gaussian process by the list of hypotheses of their probabilities. And then what the model does, it basically updates the probability of the model, updates the priors of the model, and then it also suggests the next point in your parameter space where you can learn fastest. So in some sense, it gives a reward to the model with the lowest predicted probability. And the trick here is that we expect that if we have the right physical model of the phenomenon, that it has the best predictability. And if we have the wrong model, then the predictability is worse. So we put these things together. And this is just an illustration of some abstract process, how if we have 3 models and model 3 is correct. So as normal in reinforcement learning, we introduce the epsilon greedy policy to sample the models if we are not sure what they are. So the model explores model number 1. It's not the best one. It uses the epsilon greedy to sample model 2, not the best one. Then at some point, it locks on the model 3 as the right one. It explores other ones to make sure that you are still in the right. But this is kind of a classic combination of BO plus the RL type of approach. Can it work? So let's start with the combinatorial library. So this is, I'm going to show you several experiments that are of the type that they are done once because you have to, and then I hope that nobody has to repeat them again because very often you have to deal with the setup. So this is one of those experiments. So this is the case when Yongtao Liu, who was my postdoc at that time and now staff member at CNMS, basically done the manual hypothesis learning experiment on the combinatorial library. So in this case, you can see the difference in the domain structures. You can see the systematic evolution of the domain loops. And working with Anna Morozovska, we come up with the 2 competitive models, so corresponding to the first and second order phase transition. So this is a manual hypothesis learning experiment. So 2 things. First of all, it didn't work because even though we see that one model ended up slightly better than the other one, to be honest, both of them are horrible. So in fact, our data shows that there is an increase of signal, but both of them predict that there will be a decrease. So it didn't work very well. Secondly, running a automated experiment using human operator is something that ideally should be done only once and no more, because you do it to make a proof of concept, but that's not the right way of doing things. Then half a year later, when the instrumentation became a little bit better integrated with the ML, we started to run another experiment where we start to go back to ferroelectric domain switching, right? You always go back to the area where you come from. The nice thing about the ferroelectric domain switching is that we have well-defined parameter space. It's the pulse length and pulse magnitude, only 2 parameters. And also, since I've been working in this field for quite a while, we can summarize what are the hypotheses. So we have a tip, we apply bias-induced domain formation. So the domain size can be limited, can be determined by the thermodynamic of switching. There are two limiting cases here, but basically there is no time dependence, only voltage dependence. The domain size can be limited by the spinning of the domain ball when it moves in the random media, or it can be limited by the charge injection. So the domain cannot switch until we inject charge on the surface. So we have hypothesis, we have parameter space, and this is how these things work together. So I think this is the first example of fully autonomous physics discovery system. So this is the microscope connected to the ML algorithm. So the experiment here is that ML algorithm tells the microscope what bias pulse apply to the sample. So this is the process of the bias application. Then after you apply the bias and create domain, the microscope switches to the scanning regime. When you scan this region to determine the domain size, then the simple computer vision algorithm determines what the size of the domain is. Then this domain size goes back to the algorithm. So now it's on the standby after the end of the scan. So we have the domain, we determine the size. Now we provide the input to the algorithm, and then algorithm start to figure out what should be the next parameters. And when algorithm is calculating, the microscope itself kind of deletes the domain and prepares for next experiment route. So you write a domain, analyze the result, delete the written regions, write another domain, and then you repeat this experiment for several times. This is how the output looks like. So this is our parameter space. So pulse lengths can vary from 10 milliseconds to 100 seconds. This is our bias pulse magnitude. And this is how we explore this parameter space. So this is the exploration of it. This is how the SPM signal look like. This is the machine version. This is the analysis of domain size. This is we see how which of the models is actually correct. So basically what is done here is actually the example of the robotic scientist. So we have 4 competing hypotheses. They represent the full set of possibilities for the system. So that's we know from domain expertise. And then microscope chooses to run an experiment to figure out which of these hypotheses is correct. And that's kind of felt pretty good, pretty interesting. Now you can ask a question, does it mean that in 3 years there would be ChatGPT running the microscope and all of us have nothing to do? So answer is absolutely not. So let me explain why. So first of all, notice that you know this principle that when you're in the army, the soldiers think about, or lieutenants think about tactics, majors think about strategy, and generals think about logistics, right? So ultimately, you think about how to get things in the right place at the right time. So when it comes to application of machine learning in experiment, the question that we eventually will come to is, what is the reward for doing this experiment? What do I learn? Why this information is important? How what I learn going to affect other people? How the technology or understanding that I develop going to contribute to something that human can do? So it's not something, to be honest, that you need to think about when you just start, but at some point this type of issues arise. So this has become the question of the reward system, and the reward is extrinsic to the experiment. The way I configure the automated experiment to understand the role of dislocations in mechanical behavior of material would be different than understanding direct mechanical properties. It would be 2 different experiments. So reward is external, and I need to communicate it to the experiment setup. Secondly, experiments use a lot of prior knowledge. So you need to understand the physics on some level, and it's absolutely not easy to communicate it to the ML algorithm. And then during the experiment, the way the things are shaping out is that the fast decisions and low-level decisions have to be run by the AI, but the slow decisions and high-level decisions have to be done by human. So that's kind of a whole new area of explainable and human-in-the-loop experiments. So just to finalize, what if I want to do it myself? So as I mentioned, the ML is grounded in the culture of code sharing. So the codes and many of the tutorials are out there. And thank you for your attention.
Questions?
Great talk, Sergei. Good to see you here. So maybe a little bit of like a provocative question, but to some extent, you can think of machine learning as trying to decrease the time to discover, right? Make
Yeah.
that time faster. And from an experimental side, the characterization times are actually usually relatively fast compared to the material synthesis and processing time. You know, the time to when you get a sample that will work really nicely in the microscope under the SPM or whatever it is. Can you comment a little bit about applying these tools to synthesis and processing science?
Absolutely. So as I said, one of the most obvious and immediate approach is the use of the combinatorial library, because in this case you synthesize multiple materials at the same time, and all of a sudden your bottleneck is not synthesis but actually characterization. Notice that combinatorial library is not limited to composition. For example, I can easily make a combinatorial library where there is a temperature gradient across a kind of temperature gradient, or I can have a sufficiently big wafer where I have a set of lasers in such a way that each region has a different thermal history. So it can be not even the annealing temperature, but it can be annealing history encoded at different spatial locations. So that's the most obvious one. The second one, let me see if I have this slide here, which I probably don't. The second one is, let me show the yesterday slide. Come on, 1 second. The second issue is the general principle of why we're using the microscopy during material synthesis, right? So imagine that you're in the lab that wants to synthesize hybrid peroxide, or as it may be battery material, or kind of choose your preferred area. So generally, the lab will operate using the sequence of operation, like in the hybrid peroxide, make a library of microcrystals and study their properties, grow crystal, make film, and study film. So microscopy is one of the elements how you get a feedback to this workflow. So the problem that I didn't talk about today, but I talked about yesterday, that interests me is how do you create the feedbacks from the information that you get from the observational data into the optimization of the synthesis condition for the reagent. If the process is very expensive and the rate of the feedback is very small, very slow. So typical example, imagine that you have a gigafactory that should produce lithium-ion battery. So making lithium-ion battery by normal process 24 steps, by 24 process is 6 steps. A battery requires a month for testing. So the feedback is very, very slow. Which basically means that this means machine learning is not going to help too much because humans actually will do much, much better. However, if you find a way to use the proxy signal that goes that process flow, for example, the optical data, Raman, whatever, you have a chance to accelerate the process. It's absolutely not easy because building the relationship of the multi-step process, building the feedbacks back to the material synthesis is a very non-trivial problem. But as I said, from my perspective, that's a very interesting problem to solve, and that's kind of something that I work on. That's kind of what makes me curious about the application of microscopy for processing science and application. So it's doable. How to do it is a different story because the method that we understand very well is the greedy optimization. So if we have a human design workflow, we know how to optimize each step. That's doable. What we don't know and have no certainty about is whether the greedy optimization of each step is equivalent to the global optimization of the workflow. I can easily give you a counterexample where it is not the case. So that's why, in some sense, fundamental science matters, because fundamental science is equivalent to the exploring multiple opportunities rather than just focusing on one point where you expect the benefit and don't see ways around it. Generally, I know how to do it on the level of 1 and 2-step workflows. How to do it at the level of the workflow, even like this one, it's what is called North Star goal. I know how to do it. I can become either very rich or very famous at both. But at the very least, I'm not going to forward my story.
Any other questions?
Thank you very much for the talk. It's super interesting. I had a question about imaging and physical differences in the image. So either SPM or tip shape might change during imaging. Is there a way for the algorithm to recognize the mismatches and go through the image or just that?
So it's an excellent question. So notice that for 15 years, I've been doing all the scaling probe microscopy. I led the program doing SPM. Then for the last 5 years, I led the program doing electron microscopy. The reason why I started to do SPEM as opposed to SPM is exactly the reason that we did. That once you have a data from the electron microscope, you have much higher veracity, or at least at that time I thought that we had much higher veracity than data from SPM because of the big state changes. So now, once we know the machine learning better, and there are more complex techniques, this problem in principle is solvable. So I don't have the solution and I don't have the working algorithm, but I can speculate that techniques such as the variant minimization can do that. Or you can come up with the scenarios when you say that your image has some level of some underpinning latent model, so your sample is always the same. This latent model emits the duration through slightly different channels. And then you can say that, okay, I believe that the character of this emission changes like a step function. So this is my physical assumption based on the knowledge of the microscope. And I want to build a Gaussian process model that allows me to analyze this process. So it's a kind of principle is that there is the same underlying reality, just my observation process changes in a stepwise fashion. So this may work. To be honest, I don't know how to realize it because similar type of problems are solved in the context of the sensor detection and multi-sensor image fusion. But for the time being, it's not a problem that I will try to solve because it's very complicated and it's much better to take the next step for the validity. However, there are some ways how it can be solved. So, but it's complicated. So when you apply machine learning in real world scenarios, something that's surprisingly easy and some simple thing that's surprisingly complicated. So the idea is to balance where you put your time and money in the scenario where you want to do something. You need to kind of balance whether the solution is to invest in amount, or the solution is to invest in the better experiment.
Okay, well, thank you so much for your talk. Thanks, Professor Kalinin. Appreciation.
Thank you.
Thanks, George. And if you have more questions, you can just come.
What was this? Ah, nice. Okay, and make sure that.
Yeah. Sergei, good to see you.
Hey, Veronica, how's life?
Crazy.
Okay, what do you think about like